Welcome to Dr. Carmenatty's channel, where we explore the frontiers of science and technology. Today, we are diving into the fascinating world of photonic supersolids and their potential to revolutionize quantum computing. If you are new here, please hit that subscribe button and ring the bell to stay updated on our latest videos. And do not forget to leave a comment below with your thoughts or questions. I would love to hear from you. Let's get started. The promise and challenges of quantum computing. Quantum computing is one of the most exciting frontiers in modern technology. Unlike classical computers, which use bits to represent information as either zeros or ones, quantum computers use qubits, which can exist in multiple states simultaneously thanks to the principles of quantum mechanics. This allows quantum computers to tackle problems like factoring large numbers or simulating complex molecules that are practically impossible for classical machines. Imagine a future where we can design new drugs or optimize global logistics in a fraction of the time it takes today. That is the dream of quantum computing. But here is the catch. Building a practical quantum computer is incredibly difficult. One of the biggest hurdles is maintaining the fragile quantum states that qubits rely on. These states are easily disrupted by their environmental phenomenon called decoherence, which wipes out the quantum information. To combat this, many quantum systems, like those using superconducting qubits, think IBM or Google, require extreme conditions such as temperatures near absolute zero, 273 degrees Celsius or 459 degrees Fahrenheit. That's colder than outer space. Keeping things at that level of coldness requires sophisticated equipment, making quantum computing expensive and complicated to scale. So how do we overcome these challenges? Enter photonic supersolids, a mind-blowing concept that might just hold the key. What are photonic supersolids? To understand photonic supersolids, let's break it down step by step. First, we need to know what a supersolid is. In physics, a supersolid is a rare and exotic state of matter that combines two seemingly contradictory properties: the rigid, ordered structure of a solid and the frictionless flow of a superfluid. Picture a crystal where the atoms are neatly arranged in a lattice, like a grid of tiny building blocks. Now imagine those atoms flowing through that lattice without any resistance, like water sliding effortlessly through a pipe. That is a supersolid, a material that's both structured and fluid at the same time. Scientists first confirmed this state in certain ultra-cold materials, like helium, but it's incredibly tricky to create. Now let's add the photonic part. When we talk about photonic supersolids, we're not dealing with atoms or traditional matter anymore. We are talking about light. Yes, photons, the particles that make up light, can be made to behave like a supersolid under the right conditions. But how do you get light, which usually zips around 300,000 kilometers per second, 186,000 miles per second, to form an ordered structure and flow without friction? It sounds wild, but recent breakthroughs have made it possible. Here's how it works. Scientists use a laser to shine light onto a specially designed semiconductor material like gallium arsenide, which has tiny ridges or patterns carved into its surface. When a photon hits this material, it can excite an electron, creating something called an excitation pairing of an electron and a hole, the absence of an electron. This exciton then interacts with other photons, forming a polariton, a quasi-particle that's a hybrid of light and matter. By carefully controlling the setup, think precise laser tuning and a structured environment. These polaritons can condense into a state where they arrange themselves into a crystal-like pattern while still flowing freely like a superfluid. That is a photonic supersolid, light acting as both a solid and a fluid at once. It's a jaw-dropping feat of quantum physics. How photonic supersolids could boost quantum hardware. So why does this matter for quantum computing? Let's connect the dots. In a quantum computer, Qubits are the building blocks of computation. For the computer to work, these qubits must stay in a coherent state, meaning their quantum properties, like superposition or entanglement, remain intact. However, as we mentioned, decoherence is a constant threat, especially in systems that interact strongly with their surroundings. This is where photonic quantum computing shines. Instead of using electrons or atoms as qubits, it uses photons. Photons have a huge advantage. They barely interact with their environment, making them much less prone to decoherence. Plus, photonic systems don't need ultra-cold temperatures. They can work at room temperature, which is a game changer compared to superconducting qubits that need those pricey refrigerators. Companies and researchers are already exploring photonic quantum computers, encoding information in properties like a photon's polarization or path. But there is a challenge. Photons are slippery little things. They don't naturally interact with each other, which makes it challenging to manipulate them or create the entangled states needed for quantum computations. That is where photonic supersolids could step in. Their unique properties, the crystalline order combined with superfluid flow, might offer a new way to control and organize photons more effectively. Imagine this. The crystal-like structure of a photonic supersolid could act like a scaffold, arranging photonic qubits in a neat, predictable lattice. At the same time, the superfluid behavior ensures that information encoded in these photons flows without loss, preserving coherence. This could make it easier to perform quantum operations, like entangling photons or guiding them through a quantum circuit. It's like giving architects a better blueprint and tools to build a quantum computer. Now, a quick reality check. This technology is still in its infancy. Recent experiments, like those from teams at the National Research Council in Italy and the University of Innsbruck, have proven that photonic supersolids exist. However, we are not yet at the point of plugging them into a quantum computer. Still, the potential is thrilling. If researchers can harness this state of light, it could lead to more stable, efficient quantum hardware down the road. Could this lower the high cost of quantum computing? Let's talk about money. Quantum computing is notoriously expensive. Take superconducting qubits as an example. They require dilution refrigerators, massive machines that cost hundreds of thousands of dollars, and guzzle energy to keep temperatures near absolute zero. Then there's the infrastructure, vacuum chambers, shielding from electromagnetic noise, and teams of experts to maintain it all. Scaling this up for practical widespread use is a financial nightmare. Photonic quantum computing already offers a cost advantage. Since it works at room temperature, you can ditch the refrigerators and the extreme cooling systems. That alone slashes the price tag and simplifies the setup. But could photonic supersolids take this even further? Possibly. For one, the tech behind photonic supersolids, lasers and semiconductors, isn't new. The photonics industry has been perfecting these tools for decades, from fiber optics to solar cells. If we can adapt this existing know-how to create photonic supersolids for quantum hardware, manufacturing could become more cost-effective. There's no need to reinvent the wheel, tweak what's already there. Plus, if supersolids improve the efficiency and stability of photonic qubits, you might need fewer resources to achieve the same computational power, further driving down costs. But there are hurdles. Creating a photonic supersolid requires precision. Think perfectly engineered semiconductors and finely tuned lasers. Scaling that up from a lab experiment to a full-fledged quantum computer won't be cheap or easy, and integrating it with current quantum architectures will take time and investment. So, while the long-term promise is lower costs, the short-term reality is more research and development spending. Beyond computing, a glimpse onto the future. Photonic supersolids are not just about quantum computing. Their unique properties could spark innovations elsewhere. In quantum simulation, they might help us model complex systems like chemical reactions or exotic materials that are too hard for classical computers to crack. In quantum communication, they could lead to better ways to transmit quantum information over long distances. Even sensors could benefit from leveraging the sensitivity of this light-matter hybrid. It's a testament to how one discovery can ripple across multiple fields. So, there you have it. Photonic supersolids, a state where light mimics the dual nature of a solid and a superfluid, could be a breakthrough for quantum hardware. By offering new ways to control photons, they might make quantum computers more stable and efficient. And by building existing photonic technology, they could help lower the sky-high costs of quantum computing, bringing us closer to a quantum future. Thank you for joining me on this deep dive. If you enjoyed it, please give this video a thumbs up and share it with anyone curious about cutting-edge science. Don't forget to subscribe to the channel for more explorations like this. I've got plenty more to share, and I'd love to hear from you. Drop a comment below with your thoughts, questions, or ideas for future videos. Until next time, stay curious.